Welcome to the instructional video about PHG's Water Quality Monitoring Program. My name is Hannah Emmons, and I'm the Chesapeake Conservation and Climate Corps member working at Patapsco Heritage Greenway this year. PHG is the managing nonprofit of the Patapsco Valley Heritage Area and is dedicated to preserving, protecting, interpreting, and restoring the environment, history, and culture of this area. Monitoring the water quality of the Patapsco watershed is a crucial part of this mission. This program is supported by the Howard County Office of Community Sustainability. I will first go over the background and goals of our ambient water quality monitoring program. I'll then go over the logistics of how this program runs. Next, I'll talk about how we monitor for each parameter, and then I'll go over how we collect the data. This program is a part of the Alliance for the Chesapeake Bay's Water Quality Monitoring Program, which is called River Trends. And River Trends is a program that provides training and equipment and technical support for organizations and volunteers collecting water quality data. River Trends is part of a larger organization called the Chesapeake Monitoring Cooperative. The Chesapeake Monitoring Cooperative is a group of 4 organizations, and they provide technical, logistical, and outreach support for volunteers. River Trends has provided us with all the equipment and training to make this program possible at PHG. So we send all of the data that we collect to the Alliance for the Chesapeake Bay, and we upload it to the Chesapeake Data Explorer, which is the data hub for all the groups that monitor with the Chesapeake Monitoring Cooperative. The data is available for use by any interested parties, including individuals, universities, and important decision makers. Our goals for this program with PHG are to identify areas in the Patapsco watershed that require special attention, including areas with degraded water quality. This will help us direct our environmental stewardship events, such as our stream cleanups and invasive species removals. We also want to educate the Patapsco community about the current state of the watershed. This will be accomplished in part by having volunteers like yourselves help us in collecting the data. We are also going to be making a map available to the public and creating report cards highlighting how human actions impact water quality and also how land use impacts water quality, just to share information with the Patapsco community. Our first year report card is now available on our website at patapsco.org. We will now get into the logistics of the program. On the day you sign up to monitor, you'll meet PHG staff at our office located at 3748 Old Columbia Pike in Old or Historic Ellicott City. There is a free public parking lot, Lot D, right next to our building and is accessed from Hamilton Street off of Main Street. On any given day, we'll monitor between 2 and 4 sites on the Patapsco, and adjacent tributaries anywhere from Woodbine, which is upstream, or Elk Ridge, downstream from our office. The exact list of sites will be provided when you sign up, but it's subject to change. Some examples of places we monitor are Daniels Dam, Avalon area of the Patapsco Valley State Park, and where Main Street crosses the river in Old Ellicott City. Volunteers should meet at 10 a.m. or a few minutes before. We'll load up equipment from the office into the vehicle to get started. Normally, you're welcome to ride with staff, but you're also welcome to follow in your own vehicle if you'd prefer. With the commute times to get between sites, we usually return to the office around 1:30. At that time, there's an optional lab experience where we titrate the dissolved oxygen samples that we collected in the field, and we check to make sure the meters maintained their calibration. That's pictured here in the photo on the slide. This process usually takes about 30 minutes, and you're welcome to stay, but it's not required, and we don't need to know ahead of time whether or not you're going to stay. Additionally, if you're interested in the details of this post-lab work, there's a second video that'll walk you through the steps of this lab process. So what are we doing when we get out to the field? We'll be collecting chemical and physical data at each site. We also occasionally collect stream samples to culture bacteria using 2 different user-friendly procedures called Coliscan Easy Gel or RCARDs. You will get more information on the latest procedures on site. For chemical data, we'll be using a probe to collect pH and conductivity data. For nitrate and phosphate, we'll be using small handheld colorimeters. We will collect water in glass bottles and chemically fix it in the field to measure the dissolved oxygen in the water. Upon return to the lab, we perform a Winkler titration method to get the final amount of dissolved oxygen. I'm going to explain what all these mean throughout the presentation. We'll also be measuring temperature using a thermometer. For water clarity, we'll be using a transparency tube. So we've gone out into the field and we've collected all this data, but why are we measuring them? In the next few slides, I'll go through each parameter and why they're important to collect and report. One parameter that's of interest when discussing human health is bacteria. Bacteria occurs naturally in fresh and salt water, and it can also enter the stream through runoff. Some bacteria are naturally occurring and it's harmless to humans, but some bacteria can potentially cause risk of harm or illness for people that recreate in the water. Pathogens from animal or human feces can seep into the water from leaking septic systems, open sewer lines, stormwater runoff, etc. We monitor for E. coli bacteria. E. coli bacteria are actually not always harmful for humans, but there are a few specific dangerous strains. The presence of E. coli bacteria is a good indicator if there are other harmful pathogens in the water. Heavy rains cause runoff that can elevate these levels of bacteria in the water to the point that it makes it unsafe for contact. The EPA threshold for E. coli is 235 colony forming units per 100 milliliters of water. And here I want to insert an important note about thresholds and long term trends. It's important that we're looking at long term trends rather than short term. Just going out to the stream one time can't tell us the health of the stream. We need to average it from all the data over a long term period and compare it to established thresholds for our region. That's the best way to get high quality information. The next parameter that we collect is pH. pH is how acidic or basic something is. 0 is the most acidic, 14 is the most basic, and 7 is neutral. The pH of a stream is going to vary based on the geology and landscape that the stream runs through. During a rainstorm, water will pick up compounds from the surface, and that affects the acidity or alkalinity of the stream. Low or high pH can allow toxic elements and compounds to become more mobile, and they become more available for uptake by aquatic plants and animals in the stream. This can create toxic conditions for aquatic life, particularly to sensitive species such as fish, like trout. Low pH can also reduce hatching of fish eggs, irritate fish gills, and it can damage their membranes. The ideal pH of a stream is going to be between 6.5 and 8.5, but this is a threshold based on averages for the whole year. The next parameters are nitrate and phosphate. Nitrogen and phosphorus are naturally occurring in fresh and salt water, and they're needed by plants and animals to survive. But too much of these nutrients is bad for the environment. The nutrients in our waterways come from storm runoff, fertilizers, animal waste, sewer systems, wastewater treatment plants, and air pollution. Eutrophication is when excess nitrogen and phosphorus cause dense plant growth, which can include algal blooms. The algal blooms set off a cascade of other effects in the stream, which can lead to the death of aquatic animals. So here's how it happens. Algal blooms block light from the water, so the other plants don't get the sunlight they need, and these plants may die. With the excess nutrients, algae goes excessively, and then when the algae dies, it sinks to the bottom and is decomposed using bacteria. This process uses a lot of oxygen, and mass decomposition depletes the oxygen that is critical for other organisms in the water. So it can cause a dead zone, where few or no animals survive because of the lack of oxygen. So again, nutrients like nitrogen and phosphorus are critical in small amounts, but excessive amounts can be detrimental to the ecosystem. The threshold for nitrite is 1 milligram per liter, and the threshold for phosphate is less than 0.01 to zero point 0.1 milligrams per liter. What that means is anything above 0.1 milligrams per liter of phosphate is going to cause accelerated plant growth and possible eutrophication. Dissolved oxygen is the measure of how much oxygen gas is in the water. Water absorbs oxygen from the atmosphere at the water's surface, where it dissolves and mixes in. Another source of dissolved oxygen in the water is algae and underwater plants releasing oxygen during their photosynthesis. Dissolved oxygen is a good measure of stream health because all organisms need it to survive. Adversely, very low dissolved oxygen is a common cause of fish kills. Different species have different dissolved oxygen requirements. Low dissolved oxygen can occur from eutrophication, which we just talked about, and also from warmer water temperatures and stagnant water. Summer is the most common time for low dissolved oxygen because warm water holds less oxygen. So, if streams are unshaded or they receive a lot of warmer overland runoff, think about runoff from a black parking lot on a hot summer day, they are more at risk for low dissolved oxygen. The threshold for dissolved oxygen is more than 5 milliliters per liter. Conductivity is the measure of how much electricity can pass through water. Like pH, it's affected by the geology of where the water flows. Bodies of water tend to have a standard range of conductivity, so any variation of this range can indicate a source of discharge or pollution coming into the stream. Salts, metals, and some other chemicals can cause the conductivity to go up. A high conductivity reading means there's a high concentration of ions or charged particles in the water, and this leads to stress on organisms, which then leads to change in species diversity. According to guidance issued in 2013, conductivity in our region should be under about 400 and is measured in microsiemens per centimeter. Temperature is a very important parameter for stream health because many aquatic organisms can only flourish under certain temperature conditions. Areas that aren't shaded can quickly vary in temperature, and higher temperatures mean water can hold less dissolved oxygen, which is critical for aquatic life. High temperatures can also lead to accelerated chemical reactions, which leads to the release of excess nutrients in the water, leading to eutrophication. Higher temperatures can also mean higher conductivity, which puts stress on the organisms. As you can see, it's all tied together and all parameters are influenced by each other. Water temperature should not exceed 68 degrees Fahrenheit, but we're going to be measuring in Celsius, which is equivalent to 20 degrees Celsius. Our last parameter is water quality. You can see me here in this photo looking through our turbidity tube, which has a Secchi disc at the bottom. So we look through the tube to see at what point can we see the Secchi disc clearly, and that determines how cloudy or not our water is. Water clarity is the measure of how much light can pass through the water. It's based on how much suspended particles and colored organic matter are in the water, and poor water clarity is caused by a combination of different sources such as stream bank erosion, agricultural runoff, construction site runoff, urban runoff, stormwater runoff, and excessive algal growth. Poor water clarity can cause water temperatures to increase because suspended particles absorb more heat, which leads to all the consequences I just mentioned into eutrophication and lots of other problems. In addition, aquatic plants can grow best with clear water because the sunlight can reach them better. Sediments in water can clog fish gills, can make it difficult for fish to see the environment and prey, and also buries and kills their eggs on the bottoms of the river. Next up, let's go over the process of the field work. So once we're in the field, we collect bacteria first, then air temperature, followed by water temperature, then dissolved oxygen, pH, conductivity, nitrite, phosphate, and water clarity. This process is not exact, but we try to follow this order to be most efficient with our time. Once we are in the field, we want to be filling out this water quality monitoring sheet that you can see here above me. It also has a backside. It's recommended that you always monitor with a partner, which won't be an issue since we'll always go together as a team. If there's bad weather or high flow conditions, we won't monitor, and we will reach out to you ahead of time. When we're in the field, we want to wear waders or closed-toed shoes or rain boots because we might have to go into the stream. Once we are in the field, we always want to collect the sample from the middle of the stream where the water is deepest and flowing. So I'm going to go over the process of measuring each parameter in the field for just a bit of preparation so you know what to expect, but this does not need to be memorized since you'll always be in the field with a trained PhD staff member. So to measure temperature, we always want to measure air temperature before water temperature because the water droplets left on the thermometer when you measure for water, it can alter the air temperature reading. We always measure air temperature out of direct sunlight and place the thermometer under a tree away from the ground. For water temperature, submerge the thermometer beneath the water, but don't submerge the entire thermometer. Wait a few minutes for the temperature to stabilize, and it shouldn't change for about 10 seconds, and that means it's stabilized. Record that reading on the data sheet. The process of bacteria sampling mostly happens in the post-field work, but we need water samples from each site. To get the most optimal water sample for bacteria, don't open the sample bottles until right before sample collection to avoid contamination of the materials. Once the sample bottle is open, immediately take a U-shaped scoop of water from the center of the flowing river and cap the bottle. Put the samples on ice in the insulated bag until we have returned to the office for the post-field work. So then for dissolved oxygen in the field, we will need to collect 2 sample bottles at each site to guard against any error. We fill 2 sample bottles of water and fix the solution using chemicals. Fixing the solution just means no more dissolved oxygen can be added to the sample water. After we fix the samples, we'll keep them and we'll take them back to the office to do post-field work, which will actually tell us how much dissolved oxygen is in the water. Measuring pH and conductivity in the field are two very simple and very similar procedures. For each, take the appropriate probe and submerge the bottom of it into the water. Wait for it to stabilize, which is when the smiley face appears and it will display a number. Record each number on the corresponding line on the datasheet. For nitrate and phosphate, the processes are essentially the same, except for phosphate, you need to wait 3 minutes to get a result, but for nitrate, you need to wait 15 minutes, which is why it's one of the first things that we want to set up when we get to each site. The last measurement is water clarity, which is also very simple, and you saw in the picture before on the water quality slide. We'll be using a transparency tube. All we have to do is move downstream and to the middle, and point the tube upstream for water to collect in the tube until it's full. If the stream is too low, we have a bucket we can use to fill and then pour into the tube. So remove the tube from the waterway and move to a shaded area, which is important to make sure sunlight isn't influencing the reading. Make sure to remove any sunglasses if you're wearing them. You will look down the tube and try to see this black and white pattern on the Secchi disc on the bottom. If you can see the pattern while the tube is completely full, then you record 115 centimeters plus on the data sheet, because if we had a longer tube, it probably would have been even more than 115 centimeters. If you cannot see the pattern, push the bottom of the tube down onto a hard surface to release water until you're able to see the pattern clearly. Read the level of the water and record that on the data sheet. It's important to note that while we always try to be as safe as possible when we're monitoring, there are some inherent risks associated with being around streams. Potential hazards include encountering irritating plants like poison ivy or having to navigate slippery or uneven surfaces. Participants should be able to walk up and down short hills and on level ground distances up to a quarter mile. Participants should be able to balance on uneven surfaces and to stand for 25 minutes at a time, and be able to bend and squat down. You'll be asked to sign a waiver before participating. So for just a few points I want to reiterate as we're wrapping up this video, none of this needs to be memorized for success in the field. You will always be with a trained PhD staff member that has gone through the training process, and they will be there to answer any questions and lead you through the process. Also, as I mentioned before, there's a second video available that walks you through the lab processes that we do back at the office after being out in the field. If you're interested, please watch it, but none of it needs to be memorized either if you want to participate in the lab processes. Please email our water quality coordinator, Mandy DeLeo, at coordinator@patapsco.org with any questions about any of this or about how to sign up. Thank you so much for watching, and we'll hope you'll join us out on the Patapsco soon.